Hello and welcome back. So continuing on with the parser, in this video, it is time for us to begin focusing on implementation. We've got this glorious test rig set up and ready to be used, but we have to have things implemented so that we can have our tests begin to pass. So in this video, we're going to kick off implementation with getting the, what do we want to get done? The selectors, properties, and string values?
Yeah, we want to get just this first test to pass. So that's just a class selector, properties, and string values. And
Okay.
that's it.
Awesome. All right, well, let's go ahead and get that implemented then.
Okay, so I'm going to start with the base parser class. And the base parser class, like you saw before, just contains a lot of helper methods that we can use to make parsing just a little bit easier. And the implementation is pretty straightforward. I'm going to start with the consume method, which just like the lexer, what the consume method is going to do is it's going to move the token stream one forward. And the reason I said that weird is because I know I said that weird, but I did that on purpose because we are actually implementing look-aheads in our code so that we can kind of buffer up access to tokens. So we're actually going to be buffering up to 5 tokens ahead before we start parsing those tokens. And how I'm going to do that is I'm going to represent that in a little array. Going to be a read-only token array called lookahead. And lookahead count is actually, I'm going to delete that field. I was probably just hitting Alt-Enter too many times. Because we don't really need it, because what we're going to do is just instantiate our lookahead array with the lookahead count as the amount of elements in the array.
Sure.
So if we ever need to know how many elements that we have, we can just do lookahead.length. I'm not going, there's some code that's going to go in here first, but the first thing I'm going to do before that is implement the consume method. So the consume method is going to just buffer another token. And it's going to be really weird how we're using this array. We're using it kind of like a circular array where we start at the 0 index, and let's say we have a look ahead of 2. Then we buffer to the first index, then we buffer to the 0th index again, then to the first index, and we kind of wrap around so that we don't have to allocate any more memory for our look-ahead array at any time. So our consume method is going to look a bit funky. Basically, we're going to say look-ahead, and then look-ahead pointer, which hasn't been implemented yet, equals lexer.nextToken. So that's how we're going to pull tokens out of the lexer. Then we're going to set our look-ahead pointer to be our look-ahead pointer plus 1, and then modulus our look-ahead.length. So this is how we get the wrapping around effect. So as you probably can guess from this, our look-ahead pointer is just going to be an integer pointing at the current index of the look-ahead array that we're looking at. So now if you remember, so we're buffering up all these elements in advance, and when we consume, we're consuming the next one in advance. So we have to start the parsing process with our look-ahead all already consumed up to how many elements it can go for. So I'm just going to say for var I equals 0, I smaller than look-ahead count, increment I, and consume. So what this will do is this will get our look-ahead array all nice and allocated with a bunch of relevant data so we can start moving forward. Our look-ahead method is just going to use our array and then just a really basic bit of math to be able to do our wraparound behavior. So the same sort of thing where we're just, when we look ahead, we want it to wrap around if we're looking ahead more elements than what's in the current array. A match is going to be just like what we saw before in our lexer. I'm going to say next type equals lookahead1.type. If next type is type, then consume. Go forward one item. Otherwise, throw a new invalid operation exception with expected token blah found blah. So we expected what we passed into match, and we found the next type method. Next type. The EOS is just going to say look ahead one type equals end of stream. So that's how our parser will know if it's reached the end of the stream. So that's it. The most of the logic here is just a little bit of simple math to get our look-ahead array to buffer up and then to slowly wrap around as we are matching or consuming additional items. And then, of course, we have this non-destructive look-ahead method that will allow us to look ahead an arbitrary length determined by the constructor argument look-ahead count. So now we can move ahead to our CGS parser and actually talk about parsing now that we've established a decent pattern of getting data out of our lexer. The parser that we're going to be implementing is going to be a recursive descent parser, which is usually the kinds of parsers that people write by hand. It's also the kinds of parsers that Antler writes. And the structure that it takes on the class that you're implementing the methods for is that every single part of your grammar, every single valid sentence in your grammar constitutes a method. And as a method gets invoked, it is allowed to invoke other methods, as in other parts of your grammar, or even itself. So the recursive descent is a very apt name because we will be slowly invoking, going deeper and deeper into the call stack, getting more and more specific about what exactly we're parsing, and it'll allow us to do recursive parsing and parsing like with loops of items such as multiple rules or multiple properties and so on. So what I'm going to start with in our main parse method is we're going to say while lookahead while not EOS rule, and it's going to autocorrect improperly. So rule is going to be the first sentence of the grammar that I'm going to expect to be valid, or I'm going to expect to parse. And so the rule is going to inevitably invoke the other sentences, other methods such as selectors and properties and all that stuff. The first thing I'm going to do is I'm going to create a style builder. Because we've entered, a rule builder. Because we've entered a rule, we want to have a rule builder that our parser can invoke actions on. It's going to be builder.createRule. Then I'm going to turn this into a field. So you see on line 8 a field just appeared to hold our rule builder while we're actually parsing out the selectors and the properties. Next thing I'm going to do is invoke the selectors method. Then I'm going to match and open curly. Then I'm going to say while lookahead1.type is not a close curly, and we're not at the end of the stream, parse out a property, and then finally match a close curly. So you see, we kind of created a little DSL basically by properly separating our sentences into methods and our basic framework that our base class provides. So this should read pretty much very well because you see they match open curly. So that means we need the first thing that after the selectors, the first thing that we need to see is an open curly. Mm-hmm. And then while we're not hitting a closed curly, go ahead and parse the property. Mm-hmm. And then at the end, eat up a closed curly. So now I'm going to start with the selectors method. The selectors method is going to first of all create a selector builder method or selector builder field object with the rule builder. So I'm going to stick that in a field up top, and I'm going to say do, and then we'll say while lookahead1.type does not equal curly, and we're not at the end of the stream. So remember, the first thing I want to parse are just class selectors. So the only thing we need to really match at this point is whether or not we see a dot. And if we see a dot, then we want to go ahead and push a class selector. So I'm going to, first of all, break it into another rule called selector. And the reason I'm doing that is once we talk about multiple selectors, the relationship that two selectors have with each other will be parsed right here. So, for example, it'll detect a white space or a comma or a just a normal or a greater than sign to determine if it's an immediate descendant or another selector altogether. But the actual meat of figuring out what selector it'll be is going to be done inside the selector method. All this is going to do is get the next token, alias it out into a variable, and then we're just going to check a bunch of stuff. So if next token is a dot, then we are looking at a class selector. So we can go ahead and do class selector. And again, class selector is the only method that we're implementing at the moment. So inside of our class selector method, we're now sitting on a dot. So we want to match a dot. This should never ever fail. Then we want to grab the ID, or sorry, we want to grab the class, because the next token that we're going to be sitting on or pointing at is going to be the identifier that our class name represents. Then we're going to match it, make sure that it wasn't a number or something stupid like that. And then we're going to say selector builder dot set class selector class. So, I mean, really, we've already kind of built this nice little hierarchy of methods and broken out the parsing into very, very manageable steps where all we do is we look ahead, determine what kind of token we're looking at, make sure that it's the token that we expected, and move forward.
Yeah, reads very well.
So the next thing we're going to do now, that's class selectors in its entirety, because once it matches the identifier, we're going to be sitting on an open curly during this test, because it's going to match this dot, it's going to match the identifier, then it's going to sit on this O curly. What's going to happen then is this method will return, this method will return, this method will end because we're sitting on an open curly. Then this while loop will be entered, which will then require us to implement our properties method. I'm going to move this guy down to the bottom. So our properties are going to be a little bit more complex, but right now I kind of only want to deal with string values. So the first thing I'm going to do is get the name. We know we're fairly certain we're sitting on an identifier. So the first thing I'm going to do is grab the name out of our look ahead text. Then I'm going to make sure what we grabbed was an identifier, because maybe it was a number or something stupid, and that would be a syntax error. Next thing we want to do is match a colon. If a colon does not follow a identifier in the name of a property, that's invalid CSS. Then the next thing we want to do is gather a list of values. Now the interesting thing about CSS is you can pretty much send any value you want of any type and of any number of them into properties. Now obviously the properties themselves are going to determine if those values are valid, but the grammar of CSS itself lets you pretty much just send in a huge space-separated list of whatever you want to a single property. Best way to represent that is going to be with a do while loop. So we're going to say do, which will grab a certain value, while the next token, which we're going to have to bring into scope in a second, is not a semi, and we're not at the end of the stream. So this will say while we're not sitting on a semicolon, which marks the end of a property, and we're not at the end of the stream, go ahead and do this again. I'm going to go ahead and bring out two local variables, one called next token, so that code works properly. It's still not defined or set to initial value yet, so you'll get that red squiggly, but the second I set it to a value, it'll go away. Then I want to go ahead and create a list of iValues that I'm going to just add items to as I parse them out. So I'm going to say next token equals lookahead1, and then I'm going to use this to determine what kind of value I'm going to push into the values list. So I'm going to switch on next token type. And we only care about strings right now. So I'm just going to match a string. And if we match a string, we're just going to add it to our values. Values add new string value. Then pass in the lookahead1 text. So that's just going to be next token.text. And then we're going to go ahead and match out a string, which this should never fail, but you never know. Then we're going to break out. So yeah, this will go ahead and match against all the string values you can possibly throw at something. What I'm going to do is I'm going to add a default case here, and I'm going to throw a new invalid operation exception. Could not parse value from token blah. Blah will be next token dot type. So that if we throw a non-supported value type at our parser, it won't sit there in an infinite loop or do something stupid. Finally, now we have our name variable filled out and we have our values variable filled out. We can go ahead and say match our semi, and then style builder, or sorry, rule builder, set property with the name and the values. So we're just delegating right off to our rule builder, and yeah, that should be good.
Cool.
So according to what I'm looking at right here, we should be ready to be able to pass the first test, assuming that there aren't any bugs in my parser or test rig. Let's go ahead and see what happens. Don't you love things like that? Expected rule entered, but found rule entered. Oh no. Let's go ahead and debug this. My equals method's probably all screwed up. Oh, shut up. There we go. So expected to match, which is rule entered, should be rule entered, which is odd because I could have sworn I implemented the rule entered method properly. Rule entered action equals. Now the only other reason why this might be failing at the moment is if if the should library isn't properly figuring out our, you know what? I think I just used the wrong one. But it says it's using the equals method. So let's go ahead and look in our immediate window and see what's happening.
Okay.
Let's say toMatch equals, or immediate window, and toMatch equals action. Well, that's anticlimactic. Okay, I'm just going to write this in a different way. Should's not acting as it should. That wasn't intended, but it was kind of funny.
Yeah, it was.
I'm going to say action, or I'm going to say toMatch equals action should be true. So this will be a little bit simpler. Then I'm going to say, of course, blah, blah, blah was expected. Found some other stuff. And pass in our expected one was toMatch. Our expected one was action, and what it was toMatch.
Mm-hmm.
So let's go ahead and run this again and see what happens, because that was dumb. Okay, sweet. So could not parse value from token semi. So we're now actually getting an interesting exception from our test rig, or from our test rig is exercising our parser enough to show a problem with our code. So let's go ahead and jump into our throw statement right here and launch a debugger. Let's see what is going on. So right now our next token type is a semi, which is odd. Look ahead one. See, we match that. Now we're looking at a semi. What's our text? This text is just a semicolon. That's bizarre. See, what should have happened when debugging problems like this, it's always helpful just to see what happens. So we get our string and we match our string. That's good. Now we should be sitting on a semi, and I think I see the problem immediately. We match the semi, but we don't go ahead and increment our next token. We don't actually look ahead one anymore. So what I'm going to do, do you see the problem?
Mm-hmm.
We're not actually setting our next token to the next token. So I'm actually just going to do, instead of next token, I'm going to use the look ahead one. So we'll always be looking at the latest token in our stream. So let's go ahead and run this test, and we get success.
Booyah. So
yeah, definitely.
So should was working right, but it just, well, wasn't going to pass.
Yeah. Anyway, so let's show something cool that we could do. Something cool that we could do is, because ReSharper will write out whatever is in our trace.writeLine, whatever we pass into that method into this window right here. We can go ahead and do some cool little debugging stuff to make our test a little bit more flexible in the future. So I'm going to jump into our test rig, and hopefully this will make the test rig a little bit more understandable too. Whenever an action is expected, I'm going to say trace trace.writeLine, and I'm going to say that, and then append on that action. And whenever an action is matched, I'm just going to go trace writeLine, and then give it a different symbol. So let's just give it the opposite, and then pass in the action that was matched properly. And then finally, when we do a run, before we invoke parse, I'm going to do a trace.writeLine dash. So the output of this should show you what's going on with our test rig really well. The first thing I'm going to do is I'm actually going to fix up our property action, so it's a bit friendlier when we're looking at it through the debugger. This is why I painstakingly implemented all the formatting operators earlier, specifically for this. So I'm going to return out a property that, and then a list of all my values. My name is going to be that, and the value is going to be string.concat, string.join on a comma, and then pass in values, select v.toString, and we should be good. So now if we run this, we should get some nice looking output that will show you what exactly the test parser is doing, or the test rig is doing. So what we do in our parser test, we say rig.rule. This pushes on a rule entered action that's expected. Then we say rule r.selector. This pushes on a selected entered action that we're going to expect. Then we push on an s.class, which puts on a class selector action that we're going to expect. And then we do r.property, which expects a property with this name and this value. So that's what you see right here. So for example, if I were to take this and turn this into strings instead of string, it's not going to match our property action. Expected true because property text property strings was expected, but founded property text property string. So hopefully that makes the test rig a little bit more understandable about how we're queuing up things that we're expecting and then actually seeing if the parser fulfills that contract.
Mm-hmm.
But let's just go ahead and run every single other test. I'm sure most of them should fail. And it looks like one of them threw it in the tailspin. So we definitely got to get these other tests to pass. But I think for now, this should be good enough, at least as the intro to implementing our parser.
Yeah, absolutely.
There was definitely a heavy amount of stuff implemented, even if the code doesn't look incredibly intimidating. Actually writing this stuff by hand really helps out figuring out the whole process of a recursive descent parser.
Yeah, absolutely. Okay, fantastic. Well, we'll go ahead and just call this something like implementation of the parser part 1, and we'll conclude this video, and we'll catch you guys back in the next video to continue with the implementation. Thanks a lot.